Hey, this is the third movie clip for week number one. Let me briefly review what we have learned for the last two movie clips. The first one was what is a semiconductor? So, in terms of resistivity, which has the unit of ohm times centimeter, the semiconductor's resistivity or conductivity lies in between resistivity or conductivity of conductors and insulators. So I have taught you the exact number for resistivity for conductor, insulator, and semiconductor. So one thing that I would like to tell you is the resistivity of silicon. Silicon is 10 to the plus 4 ohm times centimeter, which is beyond the scope of the resistivity for semiconductor that I have told you. But that's okay. Because we are going to add up a few dopant atoms or impurity for crystalline silicon material to have the resistivity of pure silicon lower and lower. Okay, the next one is I have told you the crystalline versus amorphous or polycrystalline. So once silicon atoms are well arranged and placed following a certain rule, then we can say that this is a crystalline material. Otherwise, it's amorphous. Locally well arranged but globally uh, disordered, then we can say this material is polycrystalline. Next, we have studied how to classify the semiconductor materials into three different classes: elementary semiconductor, compound semiconductor, and alloy semiconductor. Okay. And afterwards, we have learned the atomic structure of hydrogen versus silicon. So whenever we are thinking of current flow in DRAM, NAND flash memory, or CPU, GPU, the electrons which can flow current comes from the four outermost electrons of silicon atoms. Okay? So here, those four electrons are the main actors to flow current in silicon-based integrated chips. Afterwards, we have studied that how those four electrons here, there, those four electrons are roaming around uh, in a silicon structure. Okay, then I have to taught you the hybridize the 3sp orbitals. All right, now in this movie clip, let me introduce the silicon crystalline material, some details of silicon crystalline materials. Let's take a look at here. First of all, take a look at the white colored dotted line. Then you can see that a cubic structure. Okay. In this cubic structure, at each corner, at each corner, you can find a silicon atom. Okay. Here, 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 there. Okay. So you can clearly find eight different silicon atoms which are placed at each corner of cubic. What if a certain material has followed this type of rule to build up its own material system? Then we can say that this material has simple cubic, again, simple cubic structure. Simple cubic indicates uh, this white colored dotted line builds up a unicell, which is corresponding to a simple cube. Okay, so this simple cube or unicell uh, sit down next to the identical cube or identical unicell. So those unicells can build up a big chunk of crystalline material. Okay? Simple cubic structure is the simplest material system. Okay, now take a look at the atom placed on plane. So upper plane here, one silicon atom, and bottom plane, left hand side, right hand side, front and back side. Okay, so since this is a unit cell is cube, so we have a six planes. On each plane, we have a single silicon atom. Therefore, uh, in addition to the silicon atoms placed on eight different corners, six more silicon atoms are placed on each plane. What if this type of unit cell is the basic, basic unit or basic cell to build up the whole bunch of material system? And we can say that this material is based on face-centered cubic here, face-centered cubic structure. Okay. Unfortunately, crystalline silicon material used for DRAM NAND flash and CPU is not doesn't have this type of material system FCC. Okay, it has more complicated system. So, in this lecture note, you may see and find four silicon atoms that I didn't take any note. So here one, two, and three, four. Right? Those four atoms are not selected and chosen by me when I'm explaining the simple cubic and FCC face-centered cubic structure. So what are they coming from? Let's take a look at the silicon atom number one here. So this silicon atom is exactly placed on the diagonal of this unit cell or cube. And even the ratio of two distance here is 1, 2, 3. So 1/4 diagonal line, you can find a single silicon atom, which is completely included in this silicon unit cell. Okay, so the other three silicon atoms, named as number 2, number 3, and number 4. So those the four silicon atoms are completely included within a unit cell. Okay. So in addition to the face-centered cubic structure, if you add up four more silicon atoms within a unit cell, we can say that this material is based on diamond structure. So some student may raise up this kind of question. How come you are saying that diamond? We are talking about the silicon atoms, silicon system. How come diamond, the word of diamond, come from? Well, the answer is like that. What if I replace a silicon atom with a carbon atom? Then the real jewelry diamond is exactly following this diamond structure. Okay, so instead of silicon atom, if you use carbon atom in this whole, spot, I mean the eight corners, six planes, and the four diagonals, then we can make diamond. Okay, all right. Let me erase whole things and let me summary. Now, 8 corners, you will find out atom, silicon atom, and on each plane, total 6 planes, you will find out a silicon atom. 4 different diagonals, you will find silicon atoms, total 4. Okay, so this crystalline structure is named as diamond structure, and the silicon, which is used for DRAM NAND CPU, we're gonna use this silicon diamond structured silicon material. Okay, um, let me see that one more thing here. Each silicon atom has 4 nearest neighbors. So 4 neighboring silicon atoms can be found. So take a look at this silicon. Let me erase. See here, silicon atom. So on top of this silicon atom, you can find another silicon atom. And on the bottom side of this silicon atom, so 3 different silicon atoms are placed at corner of this triangular. Okay, so if I'm drawing some a few additional lines, then you can imagine the tetrahedral structure. So in this tetrahedral structure, so let me redraw it again for your convenience. I guess this electronic pen is not working well perfectly. Anyhow, so this silicon atom is placed at the center of this tetrahedral structure, and on top of it, you can find out another silicon atom, and below it, you can see that 3 silicon atoms, all of which are placed on a single triangular. Okay, so all this is a three-dimensional view of, of showing how silicon atoms are placed. But if I redraw it in two-dimensional area, then you will see this one. So for given silicon atom, on top of it, you will see another silicon atom, and below it, you will see 3 different silicon atoms. Okay, right. And as I told you, uh, single silicon atom has 4 outermost electrons, and this silicon atom has also 4 outermost silicon atoms. 1, 2, 3, 4. So these 2 electrons are shared by these 2 silicon atoms. So this bonding forced by those 2 electrons within these 2 silicon atoms can build up the covalent bonding. Okay, covalent bonding. So that's the reason why silicon atoms is a kind of very solid type material. Therefore, you can imagine that uh, all the silicon to silicon bonding is based on the covalent bonding. Okay, right. So each silicon atom should have 4 nearest neighbors, and with those 4 neighboring silicon atoms, the silicon atom at the center can build up the covalent bonding. Okay, all right. So I have explained diamond structure and simple cubic, face-centered cubic diamond structure. Okay, the next one is a lattice constant. What is it? So lattice constant indicates the side lengths of this unit cell for crystalline material or for diamond structure. So this lattice constant is denoted with a symbol A, and A for silicon crystalline material, the lattice constant is 0.543 nanometer, which is equivalent to the 5.43 angstrom. So for your information, 1 angstrom means 10 to the minus 10 meter, which is equivalent to the zero point 0.1 nanometer. So 10 angstrom is equal to 1 nanometer. Okay, right. So since we have known the lattice constant, which indicates the side length of this unit cell, so you may estimate the real number to indicate the diagonal line. So let's do this just in case. So the height of this unit cell is A, and this diagonal line indicates that, this is A, that is A, since this is cubic structure. So this diagonal line indicates the square root 2 times A. And now the diagonal line, which includes a whole silicon atom, this line, okay, the length of this diagonal line indicates the square root 3 times A, okay? And now you can calculate this distance. What does this distance mean? The silicon to silicon distance. As I told you, this whole silicon atom is placed on the diagonal line, and the ratio of the lengths, the neighboring silicon atoms to the other is 1 to 3. Therefore, the whole diagonal line is square root 3 times A. And since this silicon atom is placed on the 1 over 4, so therefore, square root 3 over 4 times A. So this value, so if you can plug in the 0.543 nanometer here, then you can estimate the minimum distance between two silicon atoms in silicon crystalline material. Okay, so whole detailed process of estimating the silicon to silicon atom distance is well described in the example of the textbook. So take a look at it again for your information. Right. And one more thing that I want to comment is BCC. BCC indicates a body centered cubic. So body-centered cubic is not described and animated in this lecture note. But once again here, body PCC structure is quite simple. So for given simple cubic structure, you can place 8 different atoms on each corner. Then uh, right at the center of this cubic, a whole completely included silicon atom is included in this unit cell. So if this structure builds up a unit cell for a certain material, then that material is based on the BCC structure, body-centered cubic structure. So this BCC structure is not well explaining how the silicon atoms are placed in silicon substrate, wafer. Okay, because the silicon crystalline material is not following PCC structure, but following the diamond structure. Okay, again, for your information, diamond structure is FCC plus what? Four more atoms on diagonals. Okay, so remember how diamond structure can be built up with uh, FCC structure with additional four atoms. Okay, so let's move on to the next slide. This is the slide that I really love for making midterm exam problem sets. How many silicon atoms per cubic centimeter are there in silicon crystalline material? So to estimate the silicon atomic density, so the answer is described here, 5 times 10 to the 22 atoms per cubic centimeters. Let's do this. Step number one is let's count the number of atoms in a unit cell. Okay, so in a unit cell means a cube. Okay, okay, so in a cube, how many silicon atoms are included in a unit cell? Again, here in a unit cell. First of all, on each diagonal, 1, 2, 3, and 4. Okay, 4 diagonals, 4 silicon atoms are completely included within this unit cell. So in a unit cell, we can claim that 4 atoms are there. Okay, that's very easy. Next one is, what about the silicon atom on corner? So on corner, since we have a 8 corner, right? 4 corners on top, another 4 corners on bottom. Can you claim that this silicon atom is wholly, completely included in a unit cell? Maybe not. Why? Because part of it is not included in a unit cell. Okay? Therefore, we can estimate quantitatively how much part of single silicon atom is included in a unit cell. So for that purpose, to make our life easier, let's do this. You can place one more unit cell on the right hand side and on the back side and one more thing here. Then this corner, at this corner, this silicon atom is placed, right? And half of it is included in this 4 unit cell, number 1, 2, 3, 4. Yes. Okay. So for given 4 unit cells, this silicon atom is shared, right, with 4 unit cells. However, still, upper part of silicon atom is not included in those 4 unit cells. You can claim that half of it, half of this silicon atom is included in those 4 unit cells. Half of it included in 4 unit cells. In other words, you know, half of it has been included in 4 unit cells. Therefore, 1/8, right? 1/8 of silicon atom is included to single unit cell. Okay. Okay. So 1/8 of silicon atom is included in a unit cell, but we have how many corners do we have for given cube? 8 corners, right? So 1/8 times 8 corners. Therefore, effectively, single silicon atom is included in a unit cell. All right. Previously, I said 4 atoms on diagonals are included in a unit cell, and effectively, 1 silicon atom is included in a unit cell. All of these, all of these are placed on 8 corners, but after following a few simple mathematics, we ended up with effectively 1 atom, right? The last thing that we have to think of in estimating the total number of atoms in a unit cell is the atoms on the face or on the plane. How many faces or how many planes do we have for a unit cell? Since this is a cubic cell, right? Therefore, we have 6 planes, 6 faces, and on each face we have a single atom. But here the question is, for given plane, say this is a top plane, at the center of the plane, the silicon atom is placed. But only half of it, right? Half of it is included in this unit cell. The other half of it would be included in another unit cell, which would be placed on top of this unit cell that we are thinking of. Okay? So a single atom is not fully included in a cell. Only half of it is included in a unit cell. And the next one is, how many faces do we have for a given unit cell? We have 6 faces. Therefore, effectively, 3 atoms are included in a unit cell. Right, we're almost done. So 3, 1, and 4. So 4 plus 1 plus 3, total 8. So again, in this step number 1, now we are In this step number one, the total number of atoms in a unit cell is 8. Okay. All right. The final destination that we are looking for is the atomic density of silicon, right? So for a unit cell, we have 8 silicon atoms, but we are talking about the density. So density means the number of atoms divided by the unit cell volume. The question is, how can we calculate the unit cell volume? That's easy because the unit cell is a cubic structure and we know the side lengths A, okay? So A cubic. What is A? The number of 8.543 nanometers. In the very first movie clip, I told you that in the electron device community, we love to use centimeters as a length, and square centimeter as an area, and cubic centimeter as a volume. So we need to switch the unit into centimeter. So 1 nanometer is corresponding to the what 10 to the minus 7 centimeter. So plug in here. So volume A cubic 3 indicates 0.543 times 10 to the minus 7 centimeter cubic. Okay, and using your calculator, you can get this number 5 times 10 to the 20 silicon atoms per cubic centimeter. So now let's imagine how dense the silicon atoms exist in a unit cell or in a cubic centimeter. You know how small the 1 cubic centimeter is. Maybe if I draw it 1 centimeter like that. So in this cubic cell, 5 times 10 to the 20 atoms are there. 5 times 10 to the 20, 20, 22. Okay? It's a huge number. So in the upcoming lecture, we need to estimate how many impurity atoms, non-silicon atoms, would be included for a given volume, maybe per cubic centimeter. Can you guess what is the upper limit, upper boundary of the number of impurities in a crystalline silicon atom? You should answer that the upper limit is 5 times 10 to the 22. Otherwise, the impurity is not impurity. Impurity is the main actor, and silicon would be the impurity for those main actors. Okay, right. Uh, Let me stop here and let's have a short break time.